Welcome to Bureau Happold's Anatomy of Building Environments in the 21st Century Masterclass, Part 2, Design with Purpose and Forethought. This is the second in a series of 3 online masterclasses on decarbonising building services. I'd like to introduce you to our chair, Jason Cox, Discipline Lead at Bureau Happold.
Thank you, Vicky. Welcome, everyone. It's great to see so many people joining us for this masterclass session. And welcome back to a number of people who joined us for Masterclass 1. It's great to see you rejoining this one. I'm Jason Cox. I'm a director and discipline lead of our building environments team. Today, we will be discussing how can we design low carbon buildings that are ready for a change in use, refurbishment, and MEP system replacement. Buildings last a lot longer than their systems and plant, so embedding long-term flexibility into our buildings should be at the forefront of the design process. So, without further ado, I'll pass you on to one of our subject matter experts, Laura Smith, who can expand on our approach at Bureau Happold. Over to you, Laura.
Hi, Jason. Thank you very much for the introduction. So, as Jason said, today we're going to be thinking a little bit beyond MEP systems and really thinking about how we can help support the longevity of buildings. But just to start with a recap on the first masterclass. In the first masterclass, we covered a lot of discussion about embodied and operational energy and embodied carbon, really thinking about the benefits that we can offer by reducing both of these, and also recognizing that whilst we can reduce operational energy carbon, and we're kind of well on the pathway to doing that. And we have a number of high performance building examples today that are really driving that. We also need to make sure that we think about the whole life carbon picture, really think about the impact of embodied carbon as well. And that's a journey that is happening, but it's very much on its way, and it's sort of going to continue as we learn and grow more about our individual systems and the pros and cons of each of them in terms of embodied carbon. Another key thing that was covered in the first masterclass was really thinking about that client-centric approach and thinking about a couple of key performance indicators for carbon and how we can work at early stages to really shape building design. So this includes considering daylight availability, connections to outside, energy performance, and embodied carbon. And in Masterclass 1, we talked about a number of different tools and analytical processes that can be used to make sure that the outcomes are enabled by data, and data informs our decision making. So the key takeaways from Masterclass 1 were that it's really important to start early to unlock the luxury of choice. When we're looking at embodied carbon impact of MEP systems early in the design process, we have a lot of opportunities. We're at the point where there's still a blank sheet of paper on the table. We can choose how and when we can shape things and make it work. The further we get down the design process, the more things get locked in, the more we have to start focusing on the options that are available to us at that point in time. And really that is the key element of the second point, which is to focus on the relative difference between things you can't easily change later. So, MEP systems are hugely complex. There's often a number of different systems for different purposes. And to start early, we really need to simplify that into the big strategic choices and really think about consequential system choices that can't be easily changed in the design later. So, for example, how tall a building is, whether we've got the right ceiling voids to offer a certain ventilation strategy is something that we'd really want to talk about early on. The embodied carbon impact of different pipework materials is probably something that can come significantly later. However, it's also really important to remember that design is an interconnected web, and that in driving down embodied carbon of MEP, we also must make sure that we're not adversely impacting any other building elements, their embodied carbon, or the operational carbon impact of any of the MEP systems. So to move forward now to talk about Masterclass 2 and our topic of the day, we're going to start an MEP presentation with an architectural quote from Sir David Chipperfield. And I think this is really critical. So from a sustainability perspective and a resource perspective, I think we're going to change our attitude towards the reuse and refurbishment and the retrofitting of more ordinary buildings. And I think this will be a big shift in the next 10 years. I think this is something that is very true, and it's something that we're starting to see already. You can certainly see in terms of planning permission and general public opinion that there's a lot more need to understand why a building would need to be demolished and why it can't be retrofitted. And I think there's a real key shift into really focusing on what we can do to make sure that buildings last as long as possible, and that brings with it embodied carbon benefits and other wider sustainability benefits of really trying to work with what we've got rather than knock it down and rebuild whenever we can. So the key question for today's masterclass is, how do we factor in building reuse and refurbishment at day one? So a really good place to start on this is trying to understand why is building lifetime important. I've already covered some of those items, but really the longer a building lasts, the more we can reduce down its embodied carbon, the more flexible it's going to be in its approach, the more we can sort of have a sort of structure that works in a wider master plan or a community. Um, and it offers other benefits in terms of just really enhancing the quality of space. On an embodied carbon specific approach, the data here from the Office of National Statistics shows the percentage of building structures that we have in England based on their different years of age. So whether that be the 17% of buildings that exist that have been constructed pre-1919, or whether that's the 1945 to 1970s block, which is 21% of our overall building consumption, or whether it's the 9% that we've had new construction since 2010. I think there was a really interesting query in the first masterclass questions, which sort of started to look at, well, why do we look at a 60-year design life? Now, I don't know the exact reasons why that was chosen as the specific value, but looking at this data, you can see that actually a 60-year design life in the UK sits at about halfway point in our building ages, and actually that's probably not a coincidence. That probably is quite key. And actually we do have a number of buildings, nearly a fifth of our buildings actually are over 100 years old. So when we look at the embodied carbon impact of those buildings, there's some typical ranges in the middle of the screen here. And what they show is that whilst newer modern buildings may be, for example, somewhere between 300 or 500 kilograms of CO2 per square meter, an older building that was built in 1945, 1970s may be slightly higher, because without that focus on embodied carbon, there's probably greater materials used, greater carbon. So maybe something more like 500 to 800 kilograms of CO2. But actually, if we look at that on the amount of carbon per year since construction, we can see that actually that longer building lifetime offers a much lower average carbon per year since construction, and actually therefore maybe net lower embodied carbon over a set lifespan. Now, this gives us specific challenges for MEP systems. The nature of the type of systems that we have, with the moving parts, electronic components, different material typologies, means that our systems and plant, it doesn't have the same lifespan as those buildings. So, whilst we were seeing a fifth of the buildings that are kind of lasting over 100 years, actually we have set anticipated economic design life expectancy, which is provided to us by the Chartered Institute of Building Services Engineers, or CIBSE. And that really talks through how much we would expect a system to last, and last economically. And you can see here that different types of distribution systems, whether that be waste pipes and fittings at 20 to 40 years, ductwork, depending on material, being anything from 15 to 40 years, power sockets, maybe 15 years, that there's a range and they are significantly shorter than the building lifespan. Same again when we see primary plants, gas boilers maybe 15 to 20 years, chillers typically around 20 years, air handling units, again, 15 to 20 years, and electrical transformers, maybe 30 years. So what we're seeing here is that these systems don't last as long as the buildings that they're in. But also, I think another key message of this is that it's not just about the primary plant, it's actually about MEP equipment throughout the building, whether it be the local equipment within an individual room, such as a radiator or a fan coil unit, whether it's the distribution that's running through the building, or it's the primary plant. Each of those things will need to be replaced on a regular basis throughout a building that's being designed for a long lifespan. So, as an example, if we have a 100-year building life, then a MEP system with a 15-year life expectancy, we might look to have 6 replacements during that period. So that's 6 times we need to strip the equipment out. We need to cap off the system so that we can get access to that equipment without disrupting anything around it, physically replace it, put it back in, recommission it, get it all back set up, and then get the occupants back into the space to allow them to reuse it. So, there's a whole process required in that replacement that's going to cause disruption. It's going to require new materials, increase in embodied carbon, and it's going to require time and money and effort to plan those through. So whether it's the 15-year life expectancy, which is 6 replacements, or the 25-year life expectancy, which may be 3 replacements over that lifespan, there's going to need to be change factored in throughout the building lifespan, which really leads us to a key question, which is how do we design a building to sustainably accommodate plant and equipment replacement? So in order to answer that question, we've thought about this and we have a number of key points that we'd like to present. Each individual point, of which there are 5, is a step in the right direction to really helping to support that building longevity. The first one being making sure that we choose the right solutions. So getting the plant and equipment right is really important, making sure we know what that solution is and making sure that it's one that we believe will stand the test of time and will work with the building lifespan is really important. So some of this was covered in Masterclass 1, where it was presented that we should be choosing our systems based on both their operational and embodied carbon, so their whole life carbon impact. And what that shows is whereas a system like a chill beam might have a lower operational carbon impact, actually, when you look at it overall, something like a fan coil unit system might actually be better on a whole life basis. So really making sure we choose the right systems, we're thinking about the right approaches from day one is a really key part of starting to think about building longevity. One of the things that really factors into that is understanding what the trends are in terms of the different fuel sources that we might have at our disposal through that time. So this is the sort of carbon factor emissions data from the government sources, which do predicted data all the way through. And what this shows in grey is a sort of typical carbon emission factor for a gas boiler. It's pretty static because natural gas is a finite resource with a fixed carbon emissions factor. And then it also shows the sort of mid-green is the sort of grid electricity, showing that trending down as the grid decarbonizes, and then showing in the lighter green the impact of gas CHP displacing electricity, actually trending upwards, and something like a heat pump, which tracks as electricity as a fuel source, tracks the decarbonization of the grid. It shows that that's predicted as we move into the future to be the most low carbon source. So from this, that we can see that when we're selecting a heat pump option today compared to a gas boiler or a CHP, we're not just thinking about it today, also looking 50 years forwards, the best forecast data we have shows us that it will continue to be the right choice for a low carbon sustainable building, minimizing the risk that in 20 years' time there's going to be a different, more sustainable choice that then would question, do we wait for the lifespan of this piece of equipment, or do we replace it now and get more sustainability benefits from operational performance early on? What we also need to think about is the embodied carbon impact. So as we've moved from gas boilers to heat pumps, which is where the UK industry is going, and is a general trend, not necessarily the answer for every single building, we can see that the relative balance between operational carbon and embodied carbon has become more significant. So I think what we can see is from an operational carbon using an electric heat source, the trends that we can see from government data are that that's still going to continue the right thing to do. But I think what we can also see is that there's going to be a need to think really carefully about embodied carbon. And as more information comes online, through things like the CIBSE database of embodied carbon for different pieces of equipment and all of the other life cycle carbon assessment data, getting that on a kind of individual manufacturer by manufacturer basis will help us to really understand how we can sort of start to reduce the embodied carbon as well. So it may be that heat pumps are still the right selection, but we'll be able to make a more kind of finite, more kind of detailed evaluation between different types of heat pumps to really help to narrow that embodied carbon as well. So as conclusion to this sort of first section, we should really be trying to choose the low carbon solution that will minimize both embodied and operational carbon. The government data tells us that the decarbonisation of the national grid is going to support electricity use over natural gas. But there is a really important caveat on that, which is we need to be really important and consider the impact on the local electrical infrastructure. If you don't have the electrical capacity available in the grid and transformer upgrades, wider upgrades are needed, that may shift and require further discussion and consideration on an individual project. We also know that embodied carbon data is evolving for MEP systems. There's the CIBSE TM65 methodology, which is helping to grow the database and gather more information on specific manufacturers and specific components. And that data is really going to help us inform future solutions. So in terms of step 2 or item number 2 for consideration, in terms of really thinking about how we can design buildings and integrate their MEP systems for longevity, it's really about designing for the predicted climate. We all know it's well established that there is a climate emergency. I think one of the statistics that brings it really home to me is that if we look at all of the carbon emissions globally since 1751, actually half of those emissions have been in the last 30 years. So that really tells us that how we've been emitting carbon for the last 30 years cannot continue, and that we really do need to find ways of changing and shifting our viewpoint to really start to reduce that down. That is in quite interesting conflict with some of the consequences of climate change, where a study on the future of cooling by Oxford Martin School has suggested that the need for air conditioning is likely to triple by 2050. And one of the consequences of that is that 10 new air conditioning units are projected to be sold every second for the next 30 years. That is a huge number of new pieces of equipment that are going to be installed to help maintain comfort in buildings, but also that's a lot of material, a lot of embodied carbon, a lot of additional systems that really we should be looking to see how do we hit that balance and what can we do to try and sort of mitigate some of these impacts. So as covered and considered in Master Plan 1, one of the things that we can really do is think about our building form and think about how we can really trade off the benefits of daylight, energy, connection to outside, embodied carbon, really look at that analytically and use data to drive that forward and use that data in energy performance to try and reduce the cooling demand through the building form and all that's available. One of the other things that's really interesting to think about is that when we're looking at this retrofit and repurpose world, that actually one of the things that I think is going to become more important in the future is the ability to change the use of a building from different typologies. And this data on the screen here is a study of the non-domestic building stock in the UK at the moment, and shows exactly what percentages of each different type of building has full air conditioning, partial air conditioning, no air conditioning. So what we can see is that actually a very substantial part of our UK buildings does not have any air conditioning at all. But what we can also see is that there's different trends amongst different typologies. So, for example, if you compare education to office, you can see that education buildings have substantially less air conditioning offered to them at the moment, which says that if we work with a client at the moment and we have a university client who's building a new university building, and their expectation is we deliver something similar to what they've provided recently in terms of their current building stock and the level of provision of cooling that that has available. Well, if they ever wanted to swap and change that building into an academic office, then the chances are that it would need more air conditioning, it would need more provision, and it will be quite challenging to make that typology switch unless it's thought about in advance, because the provision in terms of ceiling heights, risers, space, plant space may not be available. So whilst we do need to think about trying to minimize the impact of cooling and minimize the amount of cooling provision we need, I think we also need to recognize that the climate is heating up. We've had a number of days in the late 30 degrees, over 40 degrees in the UK recently. So making sure that our buildings have the opportunity to accommodate any cooling needed and have user comfort is also really important. So some key takeaways from this would be that climate change will cause a significant shift in MEP demands over the next 25 years or more or sooner. And really, the more we can consider this impact at day one, then the more robust the building will be to sort of have a longevity and really withstand any need to sort of major adaptation in the future. So some of the ways that we can consider this would be designing for a robust climate scenario, making sure that we're designing for what the climate could be in 20 years' time rather than just what it's like today or what it's been like 10 years ago. We should really be thinking about whether it's appropriate to reserve external space for any future plant expansion. So if we need more cooling in the future, is there a space where we could fit it without having big changes to our building that would really make it struggle to fulfill its function? Do we have allowances for spare capacity in the system design? Can we put some more cooling in our pipe work without it being significantly bigger and not fitting in the space? And do we have a really clear spatial zoning strategy to allow us to do those upgrades with minimum disruption to the wider building? So really that's speaking to, can we close down a section of the building and make upgrades because it's clearly zoned and partitioned, or is everything all connected together to the point where actually it's very hard to try and break one thing down and sort of look at one thing at a time? It's really the whole building or nothing, and the impact that causes on net disruption. And really about whether it's appropriate to talk at early stages about any potential changes in building use and how the MEP design could help or hinder that future adaptation. So following on from that, the next thing I'd like to talk about is right space, right place. So MEP systems can take up quite a significant part of the building. It's not uncommon for the range of gross internal floor area that plant space takes up to be within 10 to 20% of a building. Also, our equipment can have very specific demands. In this picture, you can see a water tank that's very heavy, that has structural implications. It probably needs to be at a lower level. There are other things that need ready access that might need to be on a ground floor, and that might be in conflict with wider challenges, architectural, other logistics that need to happen. But really, it is very important to make sure that we can all work together and collaborate to get the right place and the right space. A really good example of this was a study that was done by REHVA, looking at the performance of different fans that sit within their handling unit. So there's a typical air handling unit on the photo on the screen. One of the key components in that is the fan, and there are two fans, one to supply air into the building, one to extract air from the building. And if we look at the comparative difference of having a 400 millimeter diameter fan in that piece of equipment with the same flow rate required, which is the bottom axis, or the amount of resistance, the pressure that it needs to push against, which is the vertical axis, then actually that difference of 100 millimeters diameter in fan size between 400 and 500 mil, because of the physics and because it's a square law, means that the larger fan provides a 30% reduction in the maximum power requirement. So the right place, right space in this context could be having 100 mil extra on the width of your air handling unit to really make sure that we can choose the right fan selection to make sure that we can really get the energy efficiency benefits from that right piece of space and that right performance of that piece of equipment. So really, there are many similar examples, but design choices can influence system efficiencies. Also, the way that distribution works through the building, whether we can get straight runs, whether things have to do complicated ups or downs, and linking back to the previous things that we've talked about in terms of demand increasing through either change of function or the external climate getting more extreme. Really, we should be designing to have right space, right place so that efficiency should not be compromised or potentially cannot be compromised in the case of building regulations and increasing stringency on energy efficiency. We also should try and anticipate that replacement equipment could be bigger than the day one equipment. And then really those first 3 points were considering a lot about design and early stage and how we work together collaboratively to really think about what a building needs. But a very key point that we need to consider is about running a building well. So there's a few cases for good maintenance. I'm sure there's lots of things that are really well considered, but I think these 4 points here really help me to put forward a strong case for good maintenance. So one of those items is the Energy Saving Trust have found that poorly maintained buildings can lead to higher energy consumption and therefore higher operational carbon, also increasing energy bills by up to 30%. The Health and Safety Executive in 2019 established that poor building conditions, including inadequate maintenance, were responsible for £1.3 billion worth of lost productivity annually. So that's things like rooms and spaces not being available because the building condition means you can't operate and you can't occupy that space. RICS also showed in 2016 that 83% of tenants stated that building maintenance had a direct effect on their satisfaction and likelihood to renew leases. Now, obviously, that has immediate financial benefits to the building owner, but also it's going to have wider strategic impacts as well. So, a renewed lease, maintaining the same tenant in the same space, is probably going to involve less system adaptation, less change, better performance. So if a new client comes in, a new tenant comes in, it's likely that they will want to adapt the building layout of an office or another type of space to their specific requirements, change things around. All of that is going to require taking away parts of the MEP system, adapting it, putting new things in. A range of that can be avoided if we can keep same tenants happy and in the same space. So overall, RICS have estimated that buildings with regular maintenance last 20 to 30% longer than those without. And that is going to have an impact on the whole building longevity. So really, the next time you kind of go and enter a plant room like this one, which is an air handling unit plant room with some ventilation in, I think a lot of you will probably look at this and just see a lot of space in the middle of the room and a bit of equipment on the sides. But really, I think what we're asking is to try and think about actually there's a bit of space here for maintenance. We can pull things out really easily from each of the pieces of equipment. We've got a bit of flexibility to expand and grow, whether that be, an office becomes a meeting room and needs more air per person, whether that's the climate's change, we need more cooling, whether that's, we're working to try and maximize the amount of efficiency that these units are offering us through getting the right size of equipment, and whether we're getting nice straight pipework runs, and that ability to swap and change things without disrupting the wider systems and the wider building. So really this space is critical for us and has a massive function, even if the kind of first impression might be that there's space available and why haven't we used it. It's actually fulfilling lots of different functions that are really integral to building lifetime and longevity, because if we can get it right in the plant rooms, then it really helps to minimize disruption around the building. So really, in terms of maintenance, designing for maintenance replacement during design processes is really critical to the long-term success of a building. And one of the key ingredients is the initial design strategy for access and space for maintenance. So my final thoughts on how we can sort of work to make sure that MEP systems support longevity in buildings is to plan for change. So we know that technology is ever growing and evolving. Hybrid working has definitely shifted how owners and occupiers of buildings think about what technology they need. Things like the electric vehicle movements coming in and trying to sort of have more capacity for electric vehicles and smart car parking is also starting to shift. So we know that there's lots of technology that's coming into buildings, and actually it's likely to increase and grow as different systems work and offer more benefits to the users of the building. However, we also need to be quite mindful with technology, because we want to say, yes, great, let's keep building and growing technology through the building lifetime. But it can be quite easy comparatively to fit small electrical cables, small IT cables into a building. And this can be at risk of really having a sort of layer upon layer upon layer approach, and trying to unpick that later can be really, really difficult and can impact the sort of wider ability to keep buildings up and running and changing individual items out. So I think we need to be mindful that even if they're small systems and cables, that actually complex systems can really limit potential to adapt buildings in the future. So in terms of really thinking about this and building longevity, new technologies and functionality is increasingly being added to the built environment. This is great, can be a really good thing. But we need to think about how this is going to impact ICT, electrical demands within a building, and make sure that there's an ability to adapt and evolve those systems to really accommodate them, rather than having solutions that involve adding in parts of cabling here and there, and then causing complexities of hard to trace, hard to find, don't quite know where everything's going, because the more complexity we have, the more challenging it's going to be to adapt and replace, the more disruption, the harder it is to keep buildings going for a good lifespan without significant needs to have complete refurbishments, or to actually look at the case for demolition rather than retrofit. So what does a building that's been designed with this purpose and forethought and consideration for really thinking about how we can work to make the building last as long as possible look like? Well, I think it really can look like anything, because it's really about the thought and the process that's been into it and the detail within the spaces. But there are a couple of interesting examples. The first of which is St George's Hall in Liverpool, which was built in 1854. And this really did show that kind of forethought, because it was the world's first air-conditioned building. At the time, there was real concerns in the Industrial Revolution about air quality, overall performance. So this is the first building that had fans, air filtration in it, and it was really thought about what the kind of current need was, but also how the world is changing and what shift was needed. So it's still fully in operation now in Liverpool, and it's really standing the test of the time. And what a new, more modern iteration of this might look like, well, it's still early days, but I think the Museum of the Future has a really good chance of being one of those spaces because they are really thinking about current needs and how we work with that. So there's been a real need as part of the museum to integrate in AI and virtual technology and really looking at how those systems are integrated in today and how that can kind of help to make sure the building can accommodate things that change in the future. So thank you, and I'll hand over to Vicky for questions.
Thanks, Laura, for a brilliant presentation, and to everyone who submitted questions. We can go through some of them on this session. So question number 1 is, what are the fundamental principles for net zero design?
Thank you, Vicky. I think this is a challenging question as there are actually quite a few different definitions of net zero carbon, which is why the UK Net Zero Building Standard is really exciting because it's been created collaboratively by a range of building organisations and experts. So for me, it's a really important principle to focus on what's practical to achieve within the boundaries of a particular project, whether that's the formal red line boundary and what systems, what low carbon technologies we can fit within the site, or whether that's the more wider interpretation of the boundary, whether it be the cost or program constraints. I think it's also really important that if carbon offsets are required, which they quite often are on building retrofit schemes, that actually there's a real key focus on really understanding what that offset is and what it entails because not all schemes are equal. So it's really important to understand in that route towards net zero carbon what it is that you've actually got and how it's actually offering you benefits as an individual building or client.
Thanks, Laura. Our next question, how do we limit embodied carbon in the MEP services hardware?
So I think the embodied carbon of MEP services is very much an evolving part of the industry at the moment. We know quite a lot about system comparisons, different minimizing distribution, but often the information that we've got in life cycle assessment tools provides benchmarks for different types of equipment. And we're not really in a place yet where we have individual equipment selections that we can choose option A or option B, and we know that option A is going to have a lower embodied carbon than option B when we're talking about a very specific type of equipment. So I think the CIBS ETM65 is a really big step forward because it's giving a clear, consistent methodology to calculate how we report and how we report embodied carbon. But as until we've got that real kind of data available that's growing every day, we really need to stick to the sort of general principles, which include selecting and maintaining equipment to extend its life as much as possible, minimize the use of refrigerants, simplify distribution systems as much as possible, and really look at trying to choose systems that minimize whole life carbon.
Brilliant, thanks, Laura. Is BREEAM still relevant?
Yes. So for me, I think BREEAM is still relevant, as well as all of the other environmental assessment methodologies. I think there has been a shift in their role over time. So I think at one point they would have been seen more as setting the standard and being real thought leadership in how to create a sustainable building. I think now they're starting to shift towards being a more integrated design part of the design process. But actually, I think we should consider this a sign of success if something is growing from being a sort of real kind of innovative approach to now being seen as part of the general way of being and is being adopted by more people, then that's a real success. But I think I'm also excited to see the next generation of guidance and assessment, whether that be the Net Zero Carbon Building Standard, TM 54 and 63, and neighbours, because all of those are giving a much better focus onto the actual in-use performance, as well as creating a sustainable design at the outset.
Thanks, Laura. Another question. What is the most critical issue that should be considered first in the design process?
So for me, I think the most critical issue to consider first is really understanding what the client wants and really trying to be able to distill their wants and needs into a kind of clear design brief. Now, this can be challenging, particularly if you've got a multi-headed client or there's a real disconnect between cost and program and what's needed to move a building forward. But in my experience, I think the most sustainable building designs that I've been involved in have had that common thread of really having that clear sense of purpose and focus from the outset. And actually, when the sustainable outcome is most effective, is when the client really starts by leading that vision and bringing a team around them that really supports it. Because whilst other factors may come in along the way, I think if it starts from that point, it really sets you up for success.
Thanks, Laura. As buildings become more intelligent, how do we better address technical obsolescence and associated cost and waste?
So I think we probably need to start by recognizing that we need to plan for technical obsolescence. I think that's definitely something that's had more recognition in general. Actually looking at what happens at the end of life for all types of systems, whether it's in the building, whether it's our phones at home, it's becoming increasingly important. And technology is increasingly evolving. It offers many benefits from better control, simpler user interfaces, or whether it's actually just that we can do more complicated things with our buildings. So I think a big challenge for me is really about understanding compatibility of software and when we do need to upgrade and change because it's offering us something new and exciting, then actually can we progressively replace technology or can we replace individual components rather than try and replace wholesale systems? Now, quite a lot of this is an industry challenge rather than a sort of individual um, designer that can influence it. But what we can do is we can try and support that movement and really sort of ask the right questions at the right time. I think another thing that we can do, particularly on buildings programs with really long um, design lives, is really think quite carefully about at what stage in the process do we need to freeze the technology selection. Because if we freeze the technology selection 5 years before construction, then actually the world changes a lot. That technology will be significantly out of date by the time it's installed and tested and commissioned. So the more we can try and select technology on those longer programs as close to the installation date and the commissioning date as possible, then the better. I think also another really key interrelated point is thinking about how we manage our virtual waste. So data storage and transmission, I believe, is now somewhere between 1 and 2% of our global carbon emissions. So I think within building design and within our own personal lives, I think we need to think about what's happening to all those pieces of data that we don't need, but we keep, and how that's contributing to carbon emissions.
Brilliant points. Thanks, Laura. Our next question. What is the most important kick-off conversation to have with integrated design teams?
So I think really it's important as often as we possibly can to be actually getting physically together around the table to have those first kick-off discussions. Often now meetings are virtual and people will pop in for their specific technical specialty and then they'll drop back out again. And what that's meaning is that we're losing some of that thread of really trying to understand what's going on around the table and really hearing what the motivations and concerns of other team members are so that we can really understand the impact of our decision on the wider project. I think this also came up in Master Plan 1 as well, Masterclass 1. So I think it is really important. And I think another part of that process as well is really thinking about how we share information. This hybrid working is a fairly new approach, and I think it does require some shifts in the way that we work. And really thinking through project stages, frozen deadlines, all those macro things that we need to think about along the way, whether it be frozen drawings, information for costing, getting all of that agreed and understood as much as possible at the kickoff really helps to release time available to have design conversations at the right time.
Thanks, Laura. Where do you see the biggest opportunities for improving energy efficiency within buildings?
So if we think in terms of wider buildings from a design perspective rather than just MEP systems, I think there are three big opportunities. Firstly, it's the form and the envelope performance. So really minimizing the amount of energy that's needed for the building through the sort of overarching design shapes can really help us create the right environment, whether that's good natural daylight, so we need less artificial lighting, or whether it's better thermal performance, so we've got less heat loss through the building. That's a really important starting point, that kind of fabric first approach. I think the second, which is one of the points I've tried to highlight today, is about really understanding the space that we need within buildings to sort of really optimize the energy efficiency performance, whether that's having enough space to put the most efficient systems in, whether that's creating the space through the building so distribution can be as simple as possible. All of that helps us to drive down the energy performance without compromising on the actual end consumption. But I think, thirdly, we do really need to think about how we're using our buildings. Again, particularly in that context of half of the carbon being used since the 1750s is in the last 30 years. So I'm personally particularly interested in the sort of energy sobriety movement which has come through in France through the French government, which has aimed to reduce their national energy consumption by 10%. And one of the key strategies that they've looked at in terms of that is actually in all government buildings they've reduced the heating set point to 19 degrees, and they're really looking at people to sort of wear thicker jumpers, eat warm food, and try and sort of adapt themselves rather than sort of expect the building to do everything in terms of comfort. So trying to find that sort of middle ground, and it seems to be fairly successful. And it is sort of representing a cultural shift, which I think that we've all been experiencing a little bit ourselves in that with the kind of increasing energy prices in the UK. I think everyone's been thinking a little bit harder about, do we need to turn our heating up in our house in winter, or do we actually put a warmer jumper on? So I think there is a cultural shift happening as well as a third point with the fabric form and with the sort of efficiency of systems. There's really a sort of cultural shift as well to looking more about our individual measures that we can take to improve comfort and reduce energy.
Thanks, Laura. How do you balance potentially conflicting occupant preferences, i.e., individual temperature control versus overall energy efficiency?
So that's always quite a challenging thing to manage. Um, as I've sort of covered a little bit in the previous question, there's the concept of energy sobriety and the cultural shift potentially that is actually putting more focus on the individual rather than overall rather than that impacting overall energy efficiency. But also that maybe works in some conditions. It maybe works in a slight reduction in heating a building and wearing a thicker jumper. It certainly doesn't work in summertime overheating, and it also wouldn't work with um, any spaces that have particularly significant younger or older populations, because they're all going to need a bit more support, and it's just not practical in the summer to compensate with clothing. um, I think what's going to be really important is actually using the data that we have at hand and the methods that we have at hand to really evaluate it in detail. So ASHRAE 55, for example, looks at adaptive comfort. It can be used to evaluate the impact of things like airspeed, um, clothing levels, um, individual kind of levels of activity, whether you're getting up and moving around versus sitting still. And I think actually using those methods to really be clear on what might be the most comfortable condition for that space is really important, particularly in any kind of specialized type of environment. And that's probably going to help to create that balance between individual comfort and energy efficiency.
Brilliant. Thanks. What strategies and best practices can you share for fostering true interdisciplinary collaboration?
That's a really good question. And I think the first step is really to listen. So I think if anyone on the masterclass today has any thoughts on how engineers can change our approach and work better, whether it's with architects or clients or wider parts of the project team, I would really welcome your thoughts and your comments. I think for me, in terms of MEP systems, it does kind of create its own complicated challenges in that the systems that we work with are quite complex in terms of just lots of different parts because we have HVAC systems, we have lightning protection, we have containment, we have rainwater. So there's quite a lot of different things happening. And actually, that can be quite a lot of ground to cover, whether that's in meetings, whether that's across the design. So I think one of the key things that we can do is potentially bring back more discussion and maybe more challenge to the way we work, which has dropped off a little bit for me in hybrid working. And because actually that really trying to talk things through and understand different motivations really helps to get the best option and really get that balance against competing demands across a project and really maximize sustainable outcomes. I think we're all very aware, most recently with the flooding that we've had in the UK and the overall climate emergency, that actually the more we can have that interdisciplinary collaboration and the more we can drive our buildings to be more sustainable, the better really. It's really important to us.
Thanks, Laura. One final question. How have you seen AI bring forward project or policy goals?
So I am starting to see AI in the industry, whether that be through tools that are being talked about within the office to check documents, or certainly interest in ways that we can automate tasks and ways that it can work as a design tool. But and there's also some really forward-thinking buildings, such as the Museum of the Future, which has robots that can welcome you with AI. But I think it's taking a longer time to really integrate into more traditional design approaches and activities. Um, I certainly think back to probably the first time that I heard AI talked about in in the sort of built environment was a DeepMind AI process for a data center that kind of made the press, which was publicizing a sort of 40% reduction in data center consumption through being able to sort of predict the the outside weather and algorithms to really look at how they could drive that down. And I'm not really aware since then that that's evolved to become a wider industry adaptation of sort of smart building technology that could be integrated throughout the whole of the built environment. It's definitely there, it's definitely growing, but it's not kind of at a place where we're full scale stepping forward and replacing the systems in all of our buildings. Um, but I think some of that is a good thing, and it's good to be integrating AI at the right pace. And that slow and steady approach could be really positive because, as we know, probably from the times when we've used different AI tools, there's a level of accuracy that's not always there, and there's a definite need to have those processes in place to check and make sure that it's giving us the right answers. So I think having that time available as it evolves and grows is really important. And I think some of these items we'll talk about a bit more in terms of new technologies, regulations, our best practices in Masterclass 3.
Brilliant way to sum up our Q&A session for today. Thanks, Laura. I'll now hand back to Jason.
Thank you, Vicky. Thanks, Laura. That was great. Again, some great questions. there is an interesting balance, I think, between designing in flexibility and longevity and over designing. So we do need to be careful about that. And I think communication is definitely the key to striking the right balance there. No doubt Laura could have spoken for a number of hours on the different aspects that we should all be thinking about and the impact design. So thank you for that, Laura. It was a really interesting presentation. Please follow the QR code on the screen at the moment to register for our final masterclass, which is Philosophy and Wisdom. This will cover the approach to design, how we get the best out of our designs, how we get the best out of BIM, and how we can use that as a tool. So that'll be really interesting. If you have any questions or you wish to discuss anything, please do not hesitate to reach out. As we said earlier, this is the second of 3 masterclasses focused on the anatomy of building services, and I really look forward to seeing you all in the final session.
Thanks, Jason and Laura, and to all our attendees today. One final point. Please do check out our podcast, Sandbox, which covers a huge variety of topics around the built environment, including urban biodiversity, retrofit, and digital twins. If you can scan the QR code on screen, it will take you to Bureau Happold's website with all of the episodes to date. Sandbox is available across all main podcast platforms, including Apple, Spotify, and YouTube. Once again, thanks for your time, and we hope you enjoy the rest of your day.